So in the last lecture we have discussed the concept of internal energy, and I introduced that when the body is at rest and we need to discuss the internal energy, then the total energy of the system is just the total internal energy, and this total internal energy is due to the kinetic energy and is the sum of the kinetic energy of the molecules plus the potential energy of the molecules and the vibrational energy of the molecules. Although the vibrational energy of the molecules can exist the when the body is at higher temperature. Okay, so now, and I discussed, I come up with the concept of what is ideal gas, and we know that for the ideal gas the main assumption is that there is no force of attraction among molecules. So when there is no force of attraction among molecules, so we have discussed in the last class that this force of attraction leads to the potential energy of the molecules, and this potential energy of the molecules, because there is no force of attraction, so there is no potential energy of the molecules. So the total energy of the system at rest, now I am again come back to the, now let's again make a system which has some molecules, and this is at rest. The velocity of this body as a whole is 0. Okay, so whatever the, if I have to write the total energy of this system, then this is just the internal energy, and we know that internal energy is the, we are considering a the assumption what we are going to discuss now, it has moderate temperature, so that vibrational energy is also 0. So the total energy of the system is the internal energy, and internal energy is the sum of kinetic energy, potential energy and the vibrational energy. Now we are because of the ideal gas, potential energy is not there because of the ideal gas assumption, and vibrational energy is not there because we are considering a moderate temperature. So the total energy of the system is just the kinetic energy of the molecule. So now when we arrive at this concept, so we will be going to discuss what is degree of freedom. So if we take a monoatomic, so if I take a monoatomic gas, so what are the example of monoatomic gas? So these are helium, argon, neon, krypton, Rn. So these are the examples of monoatomic gases. So monoatomic gases, in monoatomic gases there is one molecule, and there is, so this is the only atom, there is no bonds present between the two atoms to make one molecule. So this is itself a molecule, and so this has one atom, so it has different kinds of energies associated to this, different kinds of kinetic energy associated because of its motion. So these are, if we in a very general way, we always have 3-dimensional space. So we have x, y, z. So we have velocity in x, velocity in y, and velocity in z. So the total kinetic energy can be written as, total kinetic energy of this gas molecule is half m vx square plus half m vy square plus half m vz square, because of the additive nature of the energies. We have already discussed that there is no kinetic energy, and there is no potential energy, and there is no vibrational energy, because we are considering the assumption of ideal gas as well as the moderate temperature. So this molecule exists inside the system, and we have to write the total energy. So the total energy is just this, and so this becomes so if we wanted to know what is the degree of freedom for the case of monoatomic gases, so I can define it as the number of independent present, the number of independent terms present in the expression of total energy. And so this total energy is the total internal energy actually, or we can just say total internal energy, and present in the expression of total internal energy. So for the case of monoatomic gases, let's call it 1, the degree of freedom is 3. Okay. So now let's discuss the case of diatomic gases. So case of monoatomic gases is a bit easier, but in the case of diatomic gases, we have two molecules, we have two atoms that has some covalent bond, and which has one molecule, which forms one molecule. So the example of diatomic gases includes oxygen, nitrogen, hydrogen, and maybe others. So in case of all these examples, if let's say the system is this, and we are considering the 1 or 2 oxygen molecule, then we have this kind of system, and now we have to imagine the different kind of energy possible with this kind of system. So we are very sure that because we are considering the ideal gas, so internal energy we are saying here is just because of the kinetic energy present, and we can also say that this is the expression of essentially kinetic energy due to the molecule. So this is the configuration. So you can assume it like this. So it is one body tied with something like this, and so what are the different kind of motion that is possible? if we have to see the simple kinetic energy, if this is x, this is y, this is z, so now this is the we have two molecules and this is bonded with this pen, let's say, and now we have different kind of energy we need to imagine. So if we, let's say, rotate, if we translate in the horizontal direction, then it is the kinetic energy in the x direction. At the same time, we can have the velocity of these in y direction. So we can have, so this can go like this. So this is the kinetic energy in the y direction, and then we have this in the z direction. So these are the three energies, three simple kinetic energies that exist because of the velocity of this system, and these are half mvx square plus half mvy square plus half mvz square. So this is because of this. So in the x direction, this is because of the translation. This is in this is in z direction, and this is in y direction. Now there is another kind of kinetic energy that may exist because of the rotation. So if this is the axis of rotation, there are two bonds. So there is a possibility of rotation in along the xy plane. So if it is the xy plane, then there is it will rotate like this. So half I omega square because of this. So half I omega square because of this. So that is in y direction, and similarly this, it can rotate in this direction also. So that is some, we can say this is in z direction. So this rotational motion is in z direction. There may exist a rotation in x direction. So we have rotated like this, but in case of x direction, the moment of inertia is very small because the distance is very small, and so that terms will not come. So now for this case, the degree of freedom, if you calculate, this comes out to be 1, 2, 3. So this I can write it like this, 1, 1, 1, 1, 1. So it comes out to be total 5. So this is the case of diatomic gases. Now let's discuss the case of polyatomic gases. So in the case of polyatomic gases, let's say if we have some, let's say we have SO2 or we have SO3, we can take, there are n number of polyatomic gases, but we need to assume using this molecules. So we have this, as it's bit tricky to imagine, but I can try to make it simpler for you. So if it is, this is X, you can take different pen. So let's say this is X, this is Z, this is Y. So this molecule, let's say this is one molecule, and now three energies because of the movement, because of this, the motion of this molecule in the three direction, that is X, Y and Z. Okay, so this is, so the kinetic energy is half the usual m Vx square plus half m Vy square plus half m v square. So this is the kinetic energy because of just simple motion. Now let's look at the different kind of rotational motion that are exist. So now in this case we cannot neglect the rotational motion that we have neglected for the monoatomic gases in the x direction, because there is some significant amount of inertia present. So moment of inertia present. So now this is the rotation. So I can take so maybe I can take this. So now we have this molecule. So this one molecule is there, one molecule is there, one molecule is there. So this can rotate in one plane. So if this is let's say this is x y plane, and these are rotation, this is rotating in perpendicular to this plane, so that is the inertia in the z direction. So that is 1 by 2 Iz omega square plus, now this can also rotate in, so this is we have discussed z. Now this can also rotate in this direction, so that is x. So this is z. So this can also rotate in this y direction perpendicular to that. So that this comes out to be I z omega. So sorry, I y omega y square. Now there is, so we have discussed two motion across the two planes like this, like this. Now there exists a motion so we have discussed this, we have discussed. So now there exists a motion like this across in the x in the y z plane. So that is half I z omega z square. Okay, so now the degree of freedom comes out to be so this is the total number of terms are 1 2 3 4 5 6. So degree of freedom for the case of polyatomic gases comes out to be 6. So if you didn't understand, we can go through it again because it's a bit difficult. So for the one molecule it is easier. So this is one, and this is in x direction, y direction and z direction. So this is for one molecule. Now if we have two molecules, then this will go like this. This is in x direction, this will go in y, so that is in y direction, and this will go perpendicular to this plane, so that is z direction. And now we have to consider the rotational motion. So it can rotate about this axis, it can rotate about this axis, and it can also rotate about this axis, but that is very small. So the total degree of freedom comes out to be 5. In the last case, that is the case of polyatomic gases. If you take the example of SO2 or SO3 also, then you will get the same answer. So if we have this is a kind, so we have, so this is moving in one direction, this is moving in one direction, and this is moving in one direction. So these are the normal kinetic energies. Now the rotational kinetic energies comes out to be like this. So it can rotate in this direction, it can rotate in this direction like this, and it can rotate in YZ plane, so that is in x direction. Okay, so these are the different kind. So these are the degree of freedom that we have discussed till now. Now I have to introduce the concept of a law of equipartition of energy. So law of equipartition of energy will tell us about that how the different energies is distributed among the molecules. So I will end this discussion with this concept, that the degree of freedom, because it needs some time to understand. So try to understand it, and then in the next class we will be going to understand the law of equipartition of energy and what it states. Thank you.